Okay, yeah. We had a long break over the last weekend, and we have seen some of your activities on the web, and Mr. Kyungwon Kim uploaded the grapher, three-dimensional grapher with Excel, and it has been examined, but he must be upgraded, so we will take a look. And also Mr. Youngil Oh uploaded the SIR model with this year's Thanksgiving festival with the H1N1 influenza. So yeah, we will try to upgrade this and to see what can be done on this Thursday. Okay, now today we're gonna start with some of interesting example of Blacout game. Most of you must have seen a paper on Blacout game, and most of these 5 years old paper was appeared in the contemporary linear algebra textbook. So you must be familiar with this Blacout game using the linear algebraic algorithm. Okay, today we will briefly go through on this on rectangular on the square matrix case and rectangular cases, and also the recent advancement on Blacout game that we finalized over the summer. Okay, yeah. Since you can easily find this paper on the web, you can download it. So you can take a look, and also you can take your textbook on contemporary linear algebra to go through this introductory part of the Blacout game with the linear algebraic algorithm. The reason that I have an interest on this problem is this problem occurred from undergraduate student from our class, and then it has been grown naturally to write in a mathematical way using the knowledge of linear algebra. And also we adapted the algorithm and programming technique to find it, and also we were able to generalize it to more advanced problems. Okay, and as you know, this Blacout game was introduced in an official website of The Beautiful Mind, the movie, and it started with 3x3 block, go board or matrix. The objective of this game is to make from the given arbitrary given condition to the all black or all white by clicking one of these 9 stones. The action on each of the stones be taken as you see in this figure 3. If you click this, it changes the color of itself and others that shares the edges. If you click this center one, it changes the color from black to white, and other 4 which has the edges as joined, shares. So, for example, if this is arbitrarily given initial condition of 3 by 3 blackout game, then if you click this, then it changes the colors of these 4 stones. If you click this, then it will change the color of these 4 stones. If you click this, then it changes the color of all these 3. That makes all white. So this problem can be considered how to find the linear combination of some of those 9 actions to add it to the given condition to make it all black or all white. Okay, that can be written in a matrix form of 0, 1 matrix like this. And if the initial condition is written in a matrix form like this, then the action that we're taking on a given condition can be considered as a linear combination of these 9 actions. By adding those 9 actions to the initial value to make it all black or all white. If you rewrite it in a matrix form, as a linear system of equations, it can be written as a 9 by 9 matrix and 9 by 1 vector to solve it. If we solve this, we can easily find the solution. If you take a mode 2 arithmetic, then this will be the answer. What that means is if you click the first one and third one and fourth one and the 8th one, then it can be done like this. The one interesting thing is the determinant of this matrix, 9 by 9 matrix, is not 0, so it's non-singular. We always have an inverse matrix of this to find the solution X. Okay, those are the very basic ideas of this problem. So we added some mathematical proofs on it to make it concrete. And that algorithm was programmed like this. So if the arbitrarily given condition is like this, then it can be, it gives us the solution. If we click the first one and 5th one and the 9th one, then it's done. So at the first time, it was programmed with the C++ programs, and then it started to be generalized. Okay. Okay, now let's take a look. So, the game of the light out game or blackout game we started to study on this light out game of 3x3 size with the suggestion of one undergraduate student. And then it's been, we found the interest of it, so we continue to generalize the game. And we had the search on this game of others. And we found Anderson and Fail introduced this game about 10 years ago. And Arajo published a result on 5x5 size blackout game in Math magazine in the year 2000 under the name of How to Turn All the Light Out for 5x5 size light out game. And the year 2004, we found a linear algebraic solution for n by n matrices, n by n go board, up to 19 by 19 non-singular cases. And also we developed the tools, Java tools, on this light-out game of the size up to 19 by 19. And this is a size of real go board, Paduk-pan size. Okay. And then we also generalized the result to not only non-singular cases of the smaller size, and we generalized the case, our solution to all non-singular cases of any size. And then myself and Dr. Kim recently gave a complete solution for the 5x5 case, which some of the work was done by Rajo in the year 2000. We completed it for the size of 5x5 case, and also we generalized the results for all n by n cases, not just the the rectangular, not just square cases. We also generalized it for the rectangular cases, and also rectangular cases, square and non-squares. Okay, so now we see how it has been done. So I already explained this a minute ago, and the formulation of the game can be written in this way. The only difference of this is we now have not a square case, we have a rectangular case. This is a 3x4 Go game. Okay, if this is a given configuration, it's a given situation, initial condition, then it can be written as a 0-1 matrix like this. Okay, then for this case, clicking the one stone makes a change of itself, makes a change in color of itself and others cells that shares the edges. Okay, so this action means we just add this 0 matrix to the original initial configuration. Okay, if you click this one, then it changes the color of these 5 stones. That the corresponding 0 matrix it looks like this. So in that case, we have, for the 3x3 rectangular blackout game or light out game, we have how many actions do we have? No, we have 12. 3 by 4. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, we have these 12 actions. This is all. There's no other actions to be taken on 3 by 4 Go games. Okay, and we can think each of these matrix as a not only a 3 by 4 matrix. We can also think this one as a 12 by 1 vectors. A matrix can be always considered as a vector. So this 12 matrix can be considered as 12 by 1 vectors. Okay, so this is the mathematical modeling, formulation of the game of the rectangular blackout game. This is suppose B is a given condition, initial condition. We choose an action on some of the 12 stones. So we choose some of the action among 12 and find the linear combination of it to be added to the given initial condition to make it a all zero matrix, or all the matrix with all ones, all white or all blacks. So this is a mathematical simulation. This linear combination is equal to minus B or J minus B. This is the case that we make all white, all black, or this is the case we make it all white. Okay, so if we have this formulation, then this can be written as this, as a 12 by 12 matrix times 12 by 1 vector is equal to a vector of the size 12 by 1. Okay, so this is a linear combination of a linear system of linear system of equations like this. So this is a very easy problem of solving linear equations. The interesting thing is, even though we have a rectangular size Go game, we have a square matrix like this. So we can think singularity and non-singularity of this matrix of the size 3 times 4 by 3 times 4. Okay? So this is a 12 by 12 matrix. So for the general case, for the general blackout game of the size n by n, if the determinant of the corresponding matrix A of the size nn by nn is not equal to 0, then this linear system of equation always has a unique solution. There's no problem. So all of the previous our argument does work on this. So for non-singular matrix case, we can determine the unique solution of the general light-out game. So our observation on blackout game can be easily generalized for the rectangular blackout game. Okay, so now we can think when the matrix is singular and when those matrix A of size mn by mn is non-singular. So we make the classification. Let's find the classification. Yeah. Okay. Then we can. This is the case that so we make the note. We found the determinant of the matrix of matrix A of each of size 1 by 1, 2 by 2, 2 by 3, 5 by 5, 5 by 6, 5 by 18, 20 times 20 by 20 matrix, 24 times 24 matrix. So we found all the determinant of every size. We marked the 0 for the non-singular case. A singular case, we found 1. We marked 1 on the case where the matrix A is non-singular. Okay, but we found another interesting pattern. There are some the closing of the bars here, and we found this is also all zeros. Okay, so that means these are the point where the matrix A is singular. If we mark all this, then what do you see? What do you see? We see some patterns. You can find some patterns. So the singular matrix appeared on this first. And also, if you see, do you see? The pattern of all those blocks are same, of size of this 6 by 6. All the patterns are same, except those closing, and the patterns are exactly same. So we checked it for the larger cases, and it worked. Most of this computation was done in Mathematica software to find it. Okay, so next thing is, now we have a conjecture. The matrix A of the size mn by mn from the m by n Blacout game, and the singularity and non-singularity can be determined by those two patterns. So we have a conjecture. Okay. So we want to show it. So we also tried to make a search and another search to start our own research. So we found the answers now. Okay. So if this classification shows for the case of 3 by 3, 19 by 19, or those, the unique solution cases was done, and not unique solution case has been, the research has been started. And for the 5 by 5 case, the partial solution was given, and complete solution was given by us, and we completed it by this. Okay, so before we give the full detailed proof of this general n by n case, we introduce a little bit of the detail on the solution, complete solution for the 5 by 5 Blacout game to deal with the singular case Blacout game. Okay, these are the same. Okay, so one of the master student start to think for these 5 by 5 cases. 5 by 6. This is a singular case. So we don't have a unique solution. So he thought, if we just start to make it all the first rows are black, and then make all the second rows are black, and then just clicking this one, then this will be turned as a white, and if you click this one, that will be black. And if you click this one, that will make the above one to be a black, and if you click this one, then this will make the change of the above one here. So if you just click the down below of the white one, then you can make it the first row black, then second row black, and third row black, and fourth row black. Then you have some patterns on the last row. And we figured it out. Those patterns, how many? The patterns can be appeared. We found A, B, C, D. We found so this is the pattern of the 5, the fifth row, the very bottom one. It can be all white, and all black, it can be all white. Or some are white and some are black. So there are this many, 2 to the 5th cases. But some of them can be obtained from others. So we could classify this A and A and A, these 8 can be classified, can be obtained from one another. What that means is, if we have this, we can get this by clicking couple and others as well. That means for this pattern, we don't have to worry about. These are all the case that we can make. We can have a solution to make it all black. Okay? Black. So we found the pattern of this. If you use the conjugate class, then we can clearly see among 32, we have pattern, one class of 8. That means we have 4 different patterns. Okay. So and all the others, the others except this all white, and the others cannot be reached to all blacks except those belongs to the class A. So if we make a program, and if we start from the ones that has a solution, then we can always have a solution. So the program always can give us the solution to complete the program. Then at least the players don't have to worry about the existence of solutions, because the initial condition that will be given are always guaranteed to a problem that has a solution. So yeah, that was our idea to get rid of the complexity for the 5x5 case. With that, yeah, we developed the games, and that gives us this program. So in general, 5x5 is the case that matrix is non-singular. But with those ideas and those algorithms to make the program, then we can this is not. Then I will try to mine. Here, this is the one that we have. Here, yeah, here for 3x3, you see, here we can always find the solution to complete it. But if we use the same algorithm for 5x5, then it shows there's no solution. But with those analysis, we made this. I think we have to change the. Okay, here, this is a different program that also deals with the non-singular cases. Here, there is no solution, but still we can find the solution. How? We just like this. So for the non-singular cases, still we were able to handle. Okay. So yeah, this is the right proper address to deal with it. So for the 5 by case for the non-singular case, for the singular case, yeah, we were able to deal with it. Okay, next. So this one can be, the programming was done for the larger size, like you see here, 21 times 15. Also, this size blackout game also treated by the same algorithm and program that we have made to find the solutions like this. If we click all the green buttons here, then we can complete it. And that was not the all we have. We also generalized this blackout game to not only 2 colors. It also generalized for the 3-color games, 3-color programs. The algorithm was the same, but the only difference is we used the mode 3 arithmetic instead of mode 2. Okay, the same algorithms works. Okay, if you, I will show some more. And also, some of this part was introduced in the textbook of the contemporary linear algebra that you see. So this is before we make a conclusion, I will show the recent advancement on this. Okay, here you see. Okay, this is another generalization to complete all of our questions. Okay, you see here, blackout game, and we show that the winning condition for the general n by n blackout game that are related to the determinant of a block triangular matrix generated by a given blackout game. And also, this Fibonacci sequence are used to get the determinant of the black triangular matrix. Okay, we will analyze, we will give the analysis of the determinant of that matrix for the general n by n blackout game. As you see here, there are many different versions of and tools for the blackout game from the handy calculator, and some are on the C programs, some are Java, and there are many different. Also, you can even find those programs in the game tool in many airplanes. They have this blackout game or Othello in the monitor at the seat in the international airplane. Okay, anyway, here, this is a formulation. For suppose we have this matrix, the given conditions, then it can be written, it can be considered, this initial condition can be considered as a zero matrix, like a 0-1 matrix like this, and this can be written as this shows exactly like what you saw, shows the action that is taken on the blackout game into the 0-1 matrices. Yes, and we can make a simulation, mathematical simulation and mathematical modeling of the given blackout game, like what we did, to form a linear system of equation like this. And we have the corresponding matrix like this. Okay? And like you saw, that has a that matrix has a pattern like this. As you see, this matrix has some patterns, isn't it? They are all ones here, and super diagonals are all not all ones, but as you see, if you make it block like this, then you have this is a block tri-diagonal matrix, and also you see here. This is a block tri-diagonal matrix, and this is another block tri-diagonal matrix. You see the pattern. Okay, so you have 4 by 4 blocks like this, and also with this you have ones here and ones here down here. So we can write it in this form. We have this block. We have this block. Diagonal matrix is here, and this block super diagonal submatrix and this block sub-diagonal matrix is. So we can write this matrix in this way. Isn't it? This block matrices and this is the block identity matrices up and down here. So this is the formulation of the matrix A that we have found. Then K, this is a form of the submatrix K, and I is the identity matrix, as you know. So we want to know the all properties of this this block matrix A. Okay, so we try to do it. That's why we found the patterns that you saw. That has 2 patterns for the singularity and non-singularity. But we did the search and another search, and we found. So this is the theorem that we have shown in our previous papers, and this is the pattern that we found. You see, this is the block pattern that we had, and this is the pattern with this. So we know this conjecture. We have this conjecture. We want to show. We want to prove it. So we had the research, we had the search of other work in paper 15, and there was a result of others on this type of block matrices. And they said the determinant of this pattern matrix, this block patterned matrix, is like this. So if you take a look, this matrix T here, T11, can be a product of these matrices. Our matrix is a special case of this, the above M. Now this and this. This was our matrix. We have a much simpler matrix. So from this previous theorem, which was proved by others, in page 15, okay, we are in 15 here, Molinari in 208, the determinant of the block tri-diagonal matrices. So it was recently proved, so we could use it. We don't have to do the same thing over again. We just can start from what they proved, what they already did. That shows the importance of the search of others' work. Okay, so from this theorem, we can tell the determinant of this special matrix is like this. So now we don't have to worry about this. This is the easy part. So this is the only This is the only thing that we need to worry about. Determinant of T11. Okay, this T11 is the upper left block of size n by n in the following matrix T. So, T is this matrix. T is this matrix. Okay, and T11 is the upper left block of the product of these matrices. So T is a matrix of what? The mth power of this matrix, because the forms are same. So T is this matrix, so T11 is the upper left block of this matrix. Upper left block. That means this. Let's use this one, like this. Upper left block of this after we multiply this m's power. So let's take a look. When m is equal to 1, T11 is just minus k. If m is equal to 2, then T11 is k square minus identity. If m is equal to 4, then k4 minus 3k square plus 1. If m is equal to 7, then minus k 7th power plus 6k 5th power minus 10k 3rd cube plus 4k, like this. So yeah, we can see. We have to find some pattern from this. We have to find some patterns. Let's take a look on this. Let's just compare the coefficient. Let's just add the coefficient with absolute values. Then 1 and 2, and this 1 and 2 makes 3, and 1, 3, 1 makes 5. 1, 4, 3 makes 8. 1, 5, 6, 1 makes 13. Do you see any pattern from here? Mr. O, what do you see? This is a Fibonacci sequence. So this coefficient is a special case of the Fibonacci, general Fibonacci sequence with signs. It has alternating signs. Besides that, that's exactly the same as the Fibonacci sequence. Isn't it? Mm-hmm. So, yeah, if you make a formulation of this coefficient, yeah, we can see this. If we make the k's and i's as a the variables, then we can form this type of the linear system of equations. If you multiply this matrix times vector, then you have this. Isn't it? This is exactly the same as this series. Okay? So we found this interpretation. This can be considered as we could use the concept of Riordan array on this series of the numbers. So we could find the A sequence from the two generating functions of these two, which give us this. Isn't it nice to match it? Then the generating function for the general polynomial can be written as this. Yeah. These are the things that you could learn from the discrete math and combinatorics courses. Okay. So generating function for this can be written in this way. From here, this can be written in this way. You see, do you see the coefficient here? This generating function can be written in this way, and this coefficient exactly matches with this and this. So what do we need is a determinant of this T11. determinant of this, where this K is a matrix of this pattern. Matrix K is this tridiagonal matrix. Okay. So these all, so determinant of T11, determinant of T11 is depend on this series. Okay, so let Ki is the matrix of the size I by I times I in this form. Then determinant of this K1 and K2 and KT can be obtained in this way. From here, we can figure out the determinant of K can be listed in this way. This exactly matches with our conjecture that was found from Mathematica. With this, we developed the simulation tool for the N by N Blackout game that you saw, and also we added for the case of the singular matrix of the given N by N Blackout game. So this conclusion shows, all of our questions which was given on the Blackout game from the very beginning to the very utmost has been fully covered with this kind of mathematical simulation. One interesting thing is all of this started from the undergraduate student, just taking a simple thought of the mathematical modeling. And then it could be generalized with the utmost recent research on these areas. Okay, that makes it more interesting to us. Sure. Yes. This is. Okay. Generalized. So I think we have covered Blackout. Yeah. So now we can conclude. Yeah, so this is one good example of mathematical modeling of real world problem. And it just used knowledge on linear algebra, particularly for solving linear system of equation, and mode 2 and 3 arithmetic. And also we used our knowledge on programming and algorithm on Pascal, C, C++, and Java, and others as well. And with those background and the knowledge and our interest, we could generalize the problem. We found a way to solve and to make a conjecture, and we developed the tools to verify them. So it was a very interesting process, not only for myself, but also for the student that raised the question and make the contributions. So all of the students that was involved in this learning process made their names on the papers which was published in the line of this research. So, and the knowledge on linear algebra and some computational skills were usefully. It is well used. And also there are many things, or many possible problems of mathematical modeling all around us. I think that will that will show, that will tell you what is the one example of linear models. Okay, any questions, Mr. Lee, Mihyun? You understand? Okay, Mr. O, any questions? Yeah. Yeah. Okay. Yeah, I will add you the questions. So the Blackout game simulation for the case of the singular matrix A, and we tried to give the initial condition that has the solutions. And we programmed it in that way and added that function to the previous program that has all functions for the non-singular matrices case. Then the combined program always offer the initial condition that has the solution, then also they can generate the solution to complete the game. So that was our objective, to supply the program that works in general. Any other question? Mr. Kim?